Hello friends, I welcome you in lecture number 11 on relations. In this lecture also we will discuss one more problem on properties of relations. So we consider this example. Let R be the relation on the set of integers defined as R equal to ordered pair AB such that either A equal to B or A equal to minus B. Check whether R is reflexive, symmetric, transitive and antisymmetric. So here our relation is a set of all ordered pairs of integers A and B such that either A and B are equal or they are negative of each other. For example, 2, 2 belongs to R because A and B are both 2, and 2, minus 2 is also in R because A equal to minus B. So these are the type of elements of this relation, and we have to decide whether this relation is satisfying these four properties. First one is reflexive property. We know that relation R is reflexive if it contains diagonal elements of this type for all elements A in a given set. Here given set is Z. So it is obvious that if we consider diagonal elements, then these two components are equal, and relation R contains all those elements for which both the components are equal. So clearly R is reflexive. We can directly write that clearly for any integer A, for any A belongs to Z, ordered pair AA belongs to R. Therefore, relation R is reflexive relation, or relation R satisfies the property of reflexive. Second property we have to check is the symmetric property. So for symmetry, if we recall, to prove that relation is symmetric, we have to check that whenever AB belongs to R, BA is also in R. In other words, if A is related to B, then we have to prove that B is also related to R. So for that we start by considering two arbitrary integers. Let AB belongs to Z be such that we consider two integers such that ordered pair AB is in the given relation, that is A is related to B, and if relation is symmetric, then we will be able to show that ordered pair BA is also in R. Now AB is in R, that means either A equal to B or A equal to minus B. AB belongs to R implies A equal to B or A equal to minus B, and we want to prove that BA belongs to R. So by the definition of given relation, BA belongs to R if B equal to A or B equal to minus A. So this we can rewrite in this way. A equal to B can be rewritten as B equal to A. Similarly, A is negative of B, so I can write B equal to negative of A, and therefore this implies ordered pair BA is also present in R. So we have shown that whenever AB belongs to R, BA is also in R. This implies that relation R is symmetric. So this property is also satisfied. Now we check for transitive property. For transitive property, we will require three elements in the given set. Given set is the set of integers. Let ABC belongs to Z, and assume that ordered pair AB belongs to R and ordered pair BC belongs to R. If our relation is transitive, then we have to show that whenever A is related to B and B related to C, we have A is related to C. we have to prove that if AB belongs to R and BC belongs to R, then AC belongs to R if our relation is transitive. So first we are trying to prove this, whether we can prove this or not. If we are able to prove that AC belongs to R, then our relation will be transitive. If there is some difficulty in proving this, then we have to find out particular elements A, B, C which does not satisfy this property. So first we are trying to prove that relation is transitive. For that we assume that suppose AB belongs to R and BC belongs to R. Now if AB belongs to R, then either A equal to B or A equal to minus B. Similarly, BC belongs to R implies B equal to C or B equal to minus C. Now here there are two possibilities, either A equal to B or A equal to minus B. Now suppose we consider this A equal to B. If A equal to B, then here also we have two possibilities. So suppose we are fixing this property, suppose that we have A equal to B and suppose B is equal to C. In this case, if B equal to C, then because A is equal to B and B equal to C, we have A equal to C. And if B equal to minus C, that is second possibility, then because A and B are equal, A equal to minus C. So if we consider, if we fix this one, suppose we have A equal to B, then either B equal to C or B equal to minus C, we have A equal to C or A equal to minus C. Whenever we have B equal to C, we have A equal to C. Whenever we have B equal to minus C, we have A equal to minus C. So if A equal to B, then we have A equal to C or A equal to minus C. That means AC belongs to R. Similarly, if we consider A equal to minus B, then here also we have two possibilities, if B equal to C or if B equal to minus C. Now A is equal to minus B and B equal to C. That means this implies that A equal to minus C. Here A equal to minus B and B equal to minus C. So if I put B equal to minus C here, I will have A equal to C. So if A equal to minus B, then also I have either A equal to C or A equal to minus C. That implies that AC belongs to R. So in any case, whenever AB belongs to R and BC belongs to R, AC is also present in R, and this implies that R is transitive relation. Therefore, this property is also satisfied because we have taken arbitrary integers A, B and C, and we have shown that whenever AB belongs to R and BC belongs to R, then AC belongs to R. And last property we have to check is antisymmetry. So we recall the definition of antisymmetry. Suppose we have two distinct elements, then we can have either AB belongs to R or BA belongs to R. That is, if we have two distinct elements, then either A is related to B or B related to A. We cannot have both of these true if A and B are different elements. In other words, suppose we have AB belongs to R and BA belongs to R, then we must have A equal to B. So there are two equivalent ways to check antisymmetry. Suppose you want to prove that your relation is antisymmetric, then you start by assuming that AB belongs to R and BA belongs to R and try to show that A equal to B. And if you want to disprove that relation is antisymmetric, then you can find out two distinct elements A and B in a given set. such that AB belongs to R and BA belongs to R. So first we try to prove that relation is antisymmetric. So for that I assume that AB belongs to R and BA belongs to R. Now if AB belongs to R, then I have either A equal to B or A equal to minus B. And same thing here, if BA belongs to R, then I have either B equal to A or B equal to minus A. So in any case we can write A equal to plus or minus B. So this means we will not always have A equal to B. We may have A equal to minus B also, and we can have this satisfied, that AB belongs to R and BA belongs to R, and we can have A equal to minus B, that is A and B are different. So we are not able to prove that if AB belongs to R and BA belongs to R, then A and B are always equal. So from this we may have the idea that relation cannot be antisymmetric. So for that we have to find out two different integers such that for those two integers we have that property satisfied, that is AB belongs to R and BA belongs to R. If we can find out two different values of A and B such that A and B are different and AB belongs to R and BA belongs to R, then we can say that our relation is not antisymmetric. So we can always find out those two elements here. You can see that our relation is containing those type of ordered pairs for which either A equal to B or A equal to minus B. So you can see, if I consider this order pair 2, 2, then not 2, 2, if I consider this order pair 2, minus 2, then it is present in our relation. And if I interchange these components, I will obtain minus 2, 2. So this is also present in this relation, and 2 and minus 2 are different. This is present in this relation because this, if we consider this as A and this as B, then A equal to minus B, and same thing here. So this relation is not antisymmetric. We can write that for 2, minus 2 belongs to Z, we have 2 minus 2 belongs to Z, and minus 2, 2 is also in Z because of this property, A equal to minus B. First component is negative of second component. If I take negative of minus 2, I will obtain 2 here. If I take negative of 2, I will obtain minus 2 here. So here 2 and minus 2 are different, and 2 minus 2 as well as minus 2, 2 belongs to Z, but 2 and minus 2 are different. So this implies that relation R is not antisymmetric. So this is another nice problem. Here we have discussed that whether given relation is satisfying these four properties of relations, and we find that relation is reflexive, symmetric and transitive, but it is not antisymmetric. So this is all about this session. In upcoming sessions we will be discussing some more problems of this type. Thanks for watching.